3.5 is about approximating with tangent lines. So we're going to focus on the idea today of local linearity. And local, that idea of being really close to a particular value, and linearity, which is going to be about the idea of if I looked, let's see if I can move this picture without rotating it. There we go. If I'm looking at this quadratic and I'm looking at a line, if I'm looking at this quadratic over here, and I'm looking at the line, that line only touches the graph exactly at one point. So if I was approximating using this tangent line for x equals 0, that's a pretty good approximation. But if I was approximating for x equals 5, this tangent line is no longer a good representation or a good approximation for that value. The key thing there is how close or how local we are to the particular value that we're using to represent by this tangent line. So if I look at a quadratic and I zoom in, the closer and closer and closer I get, all three of these pictures are a quadratic. The more and more I zoom, looking at that scale factor, I know this is getting blurry, I apologize, but the more and more we zoom in, the more the function actually looks like that tangent line. The closer we get to 0, the closer that line actually is to being a good representation of our function. Again, only over that local portion that we're talking about. So what do we know about the rate of change of the tangent line and the rate of change of the function at that x value? We know that they are equal. And what we just pointed out is as we zoom in closer and closer and closer to 0, 0, our tangent line becomes a better representation of not just that one point, but points close to that one point. Remember, the further we get away, the worse or the less good of an approximation that we're looking at. So we want to be choosing values that are close to 0 in this case to make this tangent line represent more than just one particular value. And that leads us to the idea of local linearization. Local linearization allows us to approximate the value of a function by finding the point on a tangent line whose x value is very close to the value that we're looking for. This is usually most effective when we kind of have what I like to call messy functions, or when we have a value that we're evaluating at that's not going to give us a nice integer answer. We're going to see something rational or irrational. It's most effective when we have a function that is implicit or that is unwieldy, meaning it's not really easy to analyze or approximate the tangent line using what we already know. So that's the big picture idea. How can we come up with a function that's close enough and find the tangent line to that close enough function to get a good approximation? And remember, the further you move away from that particular value that is a good approximation, the further off your approximation is going to be. So now we're just going to look at a couple of examples. How does local linearization work? How do we use it? That is really the goal of the rest of these notes. So let's go ahead and look at example 1. So in example 1, we're really just going to focus on how to use the local linearization part. In the rest of them, 2 through 4, we're going to look at, okay, what does this look like from start to finish? So example 1 is really focusing on just the how to add in the new piece, and the other examples are really going to be tying in what we have been doing in previous chapters all together into this one idea of local linearization. So in example 2, we are given that f of 2 equals 3. I'm just going to make a note to myself. What that means is that 2, 3 is a point that I have that is on the graph of f, whatever f is. And that f prime of 2 is equal to negative 2. And what that means is that my slope is negative 2 at this same moment. So when x is equal to 2. Use local linearization to approximate f of 2.01. So what we're saying is we have an approximation, or we have a derivative evaluated at 2, and 2 is pretty close to 2.01. So how could we use what we know to approximate a future value? So the first thing I want to do is just give you the model that we're going to use for approximation. We have a slope, we have a point on the function, so we can create our tangent line. And that tangent line is going to be y minus 3 equals the slope at that point, negative 2 times x minus 2. This tangent line will approximate and give a decent approximation for values that are close to 2. So it is possible that I could use this tangent line to approximate what happens when x is equal to 5.2, but that's not going to be a good approximation because 5.2 is really far from 2.01. So to approximate this, what I'm going to do is I'm going to move my 3 to the other side, and since I am approximating, I'm approximating what happens when x is 2.1. I'm going to say negative 2 times, and I'm going to plug in that value, 2.01 minus 2, and then I'm just adding this 3 from over here to the other side. I'm going to plug that into the calculator. That's going to give me that y is approximately 2.98. So our approximation based on the information that we were given is 2.98. That's the process that we're going through. So we're going to be looking at a function, we're going to be looking at the slope at a particular value of that function, and we're going to be setting up a linear equation to approximate another value. Now the thing that's not great about this example is we don't actually know how good 2.98 is of an approximation because we don't have a function, we don't have anything to compare it to. So that's what we're going to focus on in the next examples. We're going to look at particular values, and my favorite, I think, example is number 3 because right after we do it, we're going to plug it in on a calculator and see how good of an approximation we have. So let's go ahead and work through a few more examples about local linearity. Number 2, the point 2, negative 2 is on the graph x squared plus y squared plus 2y equals 4. Use the equation of a tangent line passing through that point to approximate 2 different y values. So the very first thing, so I'm going to be looking at 2 different values that I'm approximating. So the first thing I need to do is come up with the tangent line that I'm going to use to approximate. So the very first thing I need to do is find dy dx. So I'm going to use implicit differentiation, and then I'm going to solve for dy dx. Why don't you go ahead and work through that, pause the video, and then see how you did. It's a good review from previous units. So when you differentiate implicitly, you're going to end up with dy dx equals negative x over y plus 1. And then we're going to evaluate that at the point that we're talking about in this problem, 2, negative 2. That's going to give us that our slope of our tangent line is 2. So then we're going to write the equation of our tangent line, y minus y1, or y minus negative 2, so y plus 2, equals our slope times x minus 2. Wow, that is a lot of 2's in this problem. So now I can use this tangent line to approximate both A and B. So for A, I'm going to say y is approximately, you need to make sure you're using an approximately symbol because we are in fact using this as an approximation. 2 times the quantity 2.1 minus 2 plus 2, that's going to give us that y is approximately 1.8. And over here, y is approximately 2 times 1.9 minus 2 plus 2, so y is approximately 2.2. So these are our 2 values for approximating the point, or approximating x equals 2.1 and x equals 1.9. Let's go ahead and look at our last 2 examples. And like I said, number 3 I think is probably my favorite, so let's give it a little bit more space. So this is where I think the idea of local linearization really comes into play. We want to approximate the square root of 26, which we know is somewhere close to 5, since the square root of 25 is 5. But we want to approximate it using calculus to come up with a better approximation than just saying somewhere near 5, which is really kind of the best that I can do at this point. So in order to do this, we first need to identify a function that represents the type of problem that we're talking about. So what we're talking about here are square roots. So I'm going to let f of x equal the square root of x. And what I just said was, which we could also rewrite as x to the power of 1/2. What I said is that we know that the square root of 25 is going to be close to the value we're looking for. So I'm going to just note that we have the point when x is 25, that y is 5. That is a point that we know exists in this function, f of x equals the square root of x. And that's going to help us approximate what we're trying to find for the square root of 26 instead of the square root of 25. So what we need to do in order to use local linearization is we now need to find our derivative. That's going to give us that f prime of x is equal to the square root of 1/2. If I differentiate that, I'm going to get 1/2 x to the negative 1/2 power, or 1 over 2 root x. You know what, I'm going to write it as 1 over 2x to the 1/2 power. Again, negative exponents are totally fine. So I'm going to evaluate that at the x value that I'm using for the point, at the x value that I know exists on f. So I know that when x is 25, f is 5. So what I want to know is when x is 25, what is f prime? So f prime of 25 is going to give me the slope of the tangent line that I'm going to come up with. So that's going to be 1 over 2 times the square root of 25, or 1/10. So now I can write the equation of my tangent line. So my tangent line is going to be y minus 5 equals 1/10 times x minus 25. So now that I have this tangent line, I can use this to approximate the square root of 26. So I want to know what happens with this tangent line when x is equal to 26. So we're going to say y is approximately 1/10 times 26 minus 25 plus 5, and this is going to be, approximately 5.1. And then what we can do is we can grab our calculator. We can hit second x squared, 26. The square root of 26 is 5.099. If you were rounding at the third decimal place, this would round up to be 5.1. So this is a very good approximation of the square root of 26. Now, if we used this exact same model to approximate the square root of 30, this still may be a decent approximation, but it's not going to be as strong of an approximation because 30 is a lot further from 25. So the further we get from the x value that is the one we're using to say we're close to this value, the further away we get, the worse the approximation is. And that's something that's really important to notice. That doesn't mean that if we were looking at the square root of 30 that this would not be a good approximation. And actually, we would kind of be debating between if we wanted to use 36 or 25 as the x value in that case. So just some things to keep in mind. Go ahead and pause the video and see if you can work through this last example, example number 4, on your own, and then unpause it and see how you did. So the very first thing you're going to do is you're going to find dy dx. So dy dx is going to end up being negative 3x squared minus y over x plus 4y to the third power. According to this problem, we're going to evaluate this at the point 1, 2, which is going to give us our slope, or our dy dx at the point 1, 2 is going to be negative 5 over 33. And I'm just going to keep going over here since I'm a little out of space. So now we can write our tangent line. Our tangent line is going to be y minus 2 equals the slope we just found times the value of x minus 1, which is the x value from the ordered pair that we started with. To approximate 1.1, which is what the 1.01, which is what the question is asking us to do, negative 5 over 33 times 1.01 minus 1 plus 2, that's going to give us our approximation, which is 1.998. Now we can use, for the second part, it says use the same info to find to find the x value when y is 2.01. So what that's saying is 2.01 is y, and that's negative 5 over 33 times x minus 1 plus 2. And if we just solve for x here, that's going to give us that x equals 0.934. So the big idea today about local linearization is using something that we are more comfortable working with to identify or approximate the value of something nearby, something local that relates to the function that we're talking about. So sometimes, like on problem 3, you're going to be identifying a function and working through that. Sometimes, like on problems 2 and 4, you're going to be given a function and working specifically within that problem. But keep in mind, the further away you get from the value that you're using as your approximation to find your slope in your tangent line, the further you are from that value, the less accurate your approximation is. Looking forward to working through some more examples with you in class. Thanks for listening.